Okay, in this video, I introduced the concept of simple machines. This lesson is definitely better done in person, but in the event that you missed class or you just need a refresher, this video should help you help understand what simple machines do and how they make work easier by changing the amount of force and distance. Now, the challenge of this particular slide here, there's a lot of writing, and it's hard for me to do writing on this particular touch screen. So I'm going to go ahead and move this thing over to this setup, and let's see if we can't try to understand how simple machines make work easier by changing the amount of force and distance. Okay, so if you've ever gotten a flat and you need to change a tire, you need to use a jack, and that's largely because of one of two reasons. Is it because you don't have the energy to lift the car, because you can't exert the force necessary to lift the car? And I think most people would understand. We simply can't exert the force necessary. So the car itself is pretty heavy. So we need to be able to have an advantage to be able to lift that car up using a machine. Now, we have 6 simple machines, and so those 6 simple machines are oftentimes studied in earlier classes. We have the lever, the wheel and axle, the pulley, the incline plane, the wedge, and the screw, sometimes called the screw jack. And so those 6 simple machines, probably studied those at some point previously. The reason I like to go through this lesson again is simply because of the connection that simple machines have with the concept called efficiency. Let's go ahead and see if we can't figure out what that means. So we need to be able to use a jack, largely because we cannot exert the force necessary to lift it. We have the energy to lift it, right? And if we think about work and energy, we know that work is just simply the product of force and distance. Now, I'm going to make this be a simple derivation where I assume the force and the distance displacement are in the same direction, that we have no variable forces or anything like that. So just our basic definition of work in the simplest sense. A transfer of energy by exerting a force through a displacement. Now, most machines are able to multiply force. They can make the force bigger, but they cannot make the work or energy bigger. They cannot make work or energy bigger. So they're not a work multiplier. They're not an energy multiplier. They are typically considered what we call a force multiplier. Now, to understand that, let's go ahead and draw a quick little schematic here. The schematic, that little box there, could represent any one of our 6 simple machines. And remember, a simple machine is something that allows us to do work more simply. So we have our basic equation of work as force times distance. Now, we typically have any kind of machine. We have an input side. This is the side that you do the work on. So you do some work maybe by turning the handle of that jack. So you're going to turn the thing around and spin that thing around here, and then this thing's going to lift up that car. So you have an input side. Sometimes we call that the effort side. And on the input side, you do some work. So on the input work, we would say that we exert some sort of force, and typically we're able to exert a small amount of force. I'm going to call that F in, but we end up doing that through a fairly large distance. So I'm using the size of those letters to help represent that force is usually small and distance is usually big. The idea here is that the distance that you might exert that force on this handlebar is pretty large. So we have a pretty large input distance, but the amount of force that you're exerting is relatively small. So we have a small amount of force, but through a really big distance. Now, what the machine does is it takes that work that we do and it changes the amount of force. Put this on as an output now. And so we would say this is the output work, sometimes called the resistance. And we can think of that output work as a fairly small distance that it goes through. So I'm going to say D out is pretty small, but the amount of force it's able to exert is quite a bit bigger. And we would call that the output work. Now, ideally, the size of the input work and the output work would be the same. So we're going to assume that that we don't have any energy losses here. And so we see the product of input force and input distance is the same as the product of output force and output distance. If I get a increased amount of force that comes at the expense of a decreased distance. And again, if you're not able to observe this lesson in class, typically we do some demonstrations that show exactly this idea. So increased force means less distance. The amount of work that you do, ideally, would be the same. We just get a bigger force with less distance. So going back to this example, you exert a small force through this really big distance. This thing is able to exert then a much larger force to lift that car, but it does so with pushing this thing up just a very small distance. Okay, so now again, demonstrations in class pretty critical here, but if you're not able to see those in class, then this video hopefully will suffice. Now the performance of a machine, I go over to this next thing here. I'm going to stay with this again for the writing needs for this video. The performance of a machine is typically described as something called a mechanical advantage. So just how useful is that machine to us? How much easier is the work made by this particular machine? So a lever, and typically in class I would use a lever demonstration to be able to show you this. And so a lever is a very common, simple machine. We often use a lever to be able to lift really heavy loads, as is shown here. So a lever always has some sort of input arm, we have some sort of fulcrum, and we have some output arm. And so let's use this as a numerical example. Ideal mechanical advantage, concept related to machines, is a ratio of distances. So if we think of any work application as force times distance, so I can take a look at the ratio of those distances to get a sense of the IMA. So let's go ahead and define that as an input distance divided by an output distance. So it's a mechanical advantage in the ideal sense is a ratio of distances dn compared to dout. As an example for this numerical value here, if you lift a 1,000 Newton boulder by exerting an effort force of 250 newtons, you push the long arm down a distance of 1 meter and the boulder lifts up 0.2 meters. So if we take a look at this fulcrum over here, that fulcrum located where it is means that when we push down with 1 meter of distance, because that fulcrum is closer to the load there, it only lifts it up 0.2 meters. And so we could say that the IMA of this lever system, a ratio of dn to dout, we would say in this case that would be 1 meter divided by 0.2 meters. And when I do that, I get 5. And of course, there's no units on that. The meters reduce out. You just get an IMA of 5. Now let's continue on. AMA is a ratio of the other quantity that's part of this product. Instead of a ratio of distances, the AMA is talked about as a ratio of forces. So the AMA is a ratio of forces. And so we can define the AMA as the amount of output force divided by the amount of input force. Now be careful here, because the AMA is a ratio of output to input, whereas the IMA is a ratio of input to output. So we got to be careful there. Sometimes students will make a mistake on that. As the example for this one is showing, you lift a 1,000 Newton boulder by exerting a force of 250 newtons. So let's go ahead and draw that over on this diagram. This thing weighs 1,000 newtons, but you're able to exert a fairly small force here. We'll say that that is a 250 Newton force. And in the operation of that machine, that makes that force bigger. It's able to increase that by up to 1,000 newtons. And it does so just simply because I've made the distance through which that force is acting a smaller value. So the AMA for this, ratio of output force to input force, would be 1,000 newtons divided by 250 newtons, and we would see that that is 4. Now what we'll see is anytime we look at machines, and I mentioned the concept of efficiency is one of the important concepts of machines that helps us understand work and energy transformations, is that we'll always see the AMA is going to be less than the IMA. Another way to say that is that the IMA is always greater than the AMA. And the reason for that is simply because we have some internal forces, internal friction, that's a part of every machine. It's always going to take away some of the work that we do and put it into non-useful forms. Now, we have a way of quantifying just how efficient a machine is. And so efficiency, always by definition, this is a very generic definition. We can use this for any kind of process. So how much do we get out versus how much do we put in? It could be studying for a test. Maybe you spend an hour studying for a test, but you have a lot of distractions. You might have a phone out, you might have the music playing, you might have someone that you're talking to on the phone, something along those lines. You might spend an hour studying, but in reality, it's only about 15 minutes worth that you get out. And so you'd say that you're 15 over 60, what is that, about 25% efficient. So efficiency always just a value, a ratio of how much we get out versus how much we put in. Well, we can talk about that in terms of machine. And when we talk about the work out, we could think of that as F out multiplied by D out, just a common definition for work. Looking at the output force, the output distance. Let's divide that by the work in, which would be the F in multiplied by D in. Now, we've learned some things about associative properties in mathematics, and instead of F out being associated with D out, I'm just going to go ahead and regroup these. I'm going to take F out and associate with F in. The reason for that is that I have something that describes how F out and F in are related. They're through the AMA. So let's go ahead and replace that F out over F in with the AMA. Now, D out can be associated with dn, and I see that d out over dn is actually the reciprocal of the IMA. And so I can then think of that next term as 1 over the IMA. And then from that, we get that the efficiency is just the actual mechanical advantage over the ideal mechanical advantage. For our example up here, we would say that the efficiency is just 4/5, or about 80% efficient. Okay, so you never get 100% efficiency. You never can. We always have some sort of internal losses. And so how efficient a machine is oftentimes very important to the way that work and energy are transferred. We know that we cannot create or destroy energy, but we can transfer it. Machines help us transfer that energy. How efficient we are tells us just how much of the energy that we expend, that work that we do, how much of that actually gets into useful work on the output. Okay, so there we go. A little bit on efficiency. Let's go ahead and take a look. I'm going to switch over to this now. I think for this is mostly just touchscreen things, so I can go ahead and show you the remainder of this lesson on this video on the touchscreen. We have 6 simple machines, and typically, again, I'll have these set up in class. And so we need to be able to look at a simple machine and be able to determine its ideal mechanical advantage just by looking at ratio of distances. So the IMA for a lever is really just a ratio of the lever arm on the input, or the effort side, so LE divided by the resistance lever arm, which would be LR. For a wheel and axle, we see that we exert some sort of force maybe on the wheel portion, and then through this inclined plane, through this wheel and axle machine, we're able to get a larger force on the resistance side, but it comes at a smaller distance. And so we could talk about the IMA as a ratio of big R to little r. So it'd be the big radius of the wheel compared to the little radius of the axle. I can also write that just as a ratio of big D to little d, and also a ratio of big circumference to little circumference. And again, I apologize that I can't write that too legibly on there, but all of those quantities, radius, diameter, and circumference, would be in the same ratio, so we could look at any one of those. Now for the pulley system, on the very bottom, a little bit harder to understand the pulley without a visual in place. And so typically we call the IMA for a pulley the number of strings, N, that are supporting that load. And so we'd say that N is equal to 1 in this particular case. That pulley is just there to change the direction of the force that I exert. If I pull down on this rope, that's able to lift up on this load. And so that pulley there is just simply to change the direction of the force. Now you notice over here I'm having a single pulley, but the way that I have that configured is that I actually have 2 ropes here that are supporting that load. And so whereas I only have one at this point, this one actually has two. So if I pull up with 50 newtons of force here, well, there's also 50 newtons of force here. And so 50 newtons here and 50 newtons there means that I actually get 100 newtons out. So I can get a 2 times multiplier for force, but it comes at the distance becoming half as great. And so we would say that the IMA for this for that pulley is 2. Now, if I have something that's looking like this, oftentimes these things are called block and tackles. We have 4 strings that are supporting that load, and so what I get is a multiplier of 4 ideally. So if I put 50 newtons here, 50 newtons is in each one of these 4 wires, which would mean I would get then 200 newtons on the output ideally. Okay, and so that would be an IMA of 4. Let's take a look at some of the other machines. Now, the inclined plane is one that we've studied a lot in class. We can understand inclined planes a lot easier just using mechanical advantage. So it's a ratio of the length of the incline, just how long that is, to the height of the incline. And so the narrower that ramp, so the longer the length of that ramp compared to the height, the easier it is to be able to lift that thing up. So if I want to lift a piano up into a room, maybe into a house over a staircase, I use a pretty long ramp to go up just a few steps, and that makes the force quite a bit easier, quite a bit less to be able to lift that thing up. The wedge is just a double inclined plane, if you will, and so the wedge is typically harder to demonstrate in class, but it's basically the same concept as the inclined plane, just using oftentimes to split wood or to hold doors, things like that. And finally, the screw jack. The screw jack, again, demonstrated, talked about in this first example over here. The screw jack is very commonly a very large IMA, and the reason for that is its basic design shows that as I move this handle through a pretty large distance, and I sort of swing that thing around in a circle, the screw only lifts up just a little bit of distance right here. So that little P there stands for something called the pitch of that screw. And so I move the handle all the way through this huge circumference, and then the screw sort of lifts us up a very small distance. The IMA is just a ratio of 2 pi L, which would be the circumference that my hand would move through, divided by P, the pitch, the distance between those threads. So oftentimes very large mechanical advantage are accomplished with the screw jack. The problem is that there's a lot of friction that is a part of these threads here. And so oftentimes you'll see that there's a lot of grease that is placed on those threads to make it so that we have as little friction as possible. Finally, this is to complete the lesson. Again, if you were in class, much easier to understand this lesson with the demonstrations and the equipment that we have around. This last slide for this video. Compound machines, oftentimes we'll see not simple machines just in isolation, but oftentimes we see compound machines that are essentially interlocked simple machines. So the common bicycle, composed of a tremendous number of simple machines, all sort of interconnected. So we can see wheel and axles in here, we can see pulleys, we can see levers, we can see screws, and so forth. The can opener consists of 3 or so different simple machines, and of course the lawnmower, we've got 4 or so simple machines that are all interconnected. So they're interlocked simple machines. Now the nice thing about compound machines is that we can get some pretty large mechanical advantages. So the mechanical advantage of each machine sort of multiplies with the other ones. If the first one makes an ideal mechanical advantage of 5, and the next one makes it 4 times greater, well, 5 times 4 would be 20, and so we can start to get some pretty large mechanical advantages. So we just multiply the IMAs together. Problem, though, is that efficiency is also a multiplier. And since the efficiency is always less than 1, the more machines that we interlock, the less efficient becomes the entire machine. And so since these numbers are always less than 1, we would say that the machine that is the least efficient is going to have a pretty large impact on the overall efficiency of that interlocked machine. So since it's sort of like a weak link idea, so the least efficient machine is going to have a really big impact. The overall machine efficiency is going to be less than the least efficient one. And so oftentimes when we interlock machines, we have to be very careful about making sure the efficiency is very great for each one of those. Let's do a quick example. Let's say that we have a piano. over here, and let's say the piano, typical piano might be 800 or so pounds, and so let's put that into newtons, make it a little bit easier for us to do our science kinds of things. So 800 pounds times 4.445 would be about 3,600 newtons. Let's go ahead and just call that. This thing has a weight, F sub g, of about 3,600 newtons. So it'd be pretty hard to be able to lift that, and wish I could write on the screen a little bit better. Let's try writing that with the mouse. It's not much better. 3,600 newtons, how heavy that thing is. There's no way I'm going to be able to lift that by hand. So in this case, what I might do is I might use interlock set of simple machines. Now, typically you wouldn't see something like this, but it's easy to demonstrate in the laboratory, just not in real life. So we have an inclined plane. It's a 4-to-1 ratio, so we would say that the IMA for the simple machine ramp is just a ratio of 4-to-1, which would be 4. And so we would get ideally a 4 times multiplication of that amount of force. Now we see the wheel and axle that I'm using here has a IMA of 5. It's a ratio of the big D to the little d, so the IMA there is 5. Now if I wanted to get the overall IMA, the IMA total for this would be 4 times 5, which would be 20. And so ideally we'd get 20 times multiplier. It'd be 20 times easier to lift that object than it would be to do it manually. But we have some inefficiencies. We see that the efficiency of the wheel and axle, we're only getting 60% out of what we put in. And for the ramp, maybe we don't have very good wheels on that piano, and there's some friction there. And so the efficiency of the ramp is 75%. So the efficiency is also multiplying. And so 0.6 times 0.75 is about 45% efficiency. Be careful, you got to make sure that the efficiencies are put in as decimals when it goes through to do that multiplication. So we'd say the efficiency is a 0.45 multiplier. Now, how does that relate to forces? Well, we know also that efficiency is a ratio of AMA to IMA. The key is to write really large here so we can see that better. So let's get the AMA. AMA is just the efficiency multiplied by the IMA. And so let's see, that'd be 45% multiplied by 20. So that means we have an actual mechanical advantage of 9. So what does that mean? I would only have to exert 1/9 the amount of force to be able to lift that thing up. So since AMA is a ratio of output force to input force, well, how hard I'd have to be able to exert a force to be able to lift this thing up would just be Fn. That would be F out over 9. And sure enough, if that thing has a weight of 3,600 newtons, then I'd only have to exert about 400 newtons to be able to move that thing up that incline. And that's because of that compound machine that's there to sort of help you make work easier to accomplish. Oftentimes we can get a larger force on the output, but it comes at the expense of a much smaller distance. And there we go. That completes this lesson. I hope it helped.